Hi boys and girls, this is lecture 6.7, the topic, bases other than E and applications. We've been discussing exponential and logarithmic functions to base E, but it is possible to have exponential and logarithmic functions to other bases. So let's talk about an exponential function to base A. If a is a positive real number where a is not 1, and x is any real number, then the exponential function to the base a is denoted by a to the x, and is defined by a to the x equals e to the natural log of a x. Notice that the definition of the exponential function to base a is in terms of an exponential function to base e. So any exponential function with a base other than e can be rewritten in terms of an exponential function to base e. If a equals 1, then y equals 1 to the x, which is 1, and that's a constant function. Now let's talk about the definition of a logarithmic function to base a. If a is a positive real number and a cannot be 1, and x is any positive real number, then the logarithmic function to the base a is denoted by log base a of x and is defined by log base a of x equals 1 over natural log of a times the natural log of x. Once again, notice that the logarithmic function to base a is being redefined in terms of the natural log. Logarithmic functions to the base a have properties similar to those of the natural logarithmic functions. Log base a of 1 is 0. If the argument of your logarithmic expression is a product, this can be separated into a sum of logarithms, log base a of x plus log base a of y. If the argument of your logarithmic expression is a term with an exponent, the exponent property says we can bring that exponent around to become the coefficient, n log base a of x. And if the argument of your logarithmic expression is a quotient, this can be separated into a difference of logarithms, log base a of x minus log base a of y. From the definitions of the exponential and logarithmic functions to the base a, it follows that f of x equals a to the x and g of x equals log base a of x are inverse functions of each other. Therefore, the properties of inverse functions will apply. Y equals a to the x if and only if x equals log base a of y. A to the log base a of x equals x for x greater than 0, and log base a of a to the x equals x for all x. Once again, we see that if we have inverse functions, composing those functions results in x. This is helpful in solving exponential and logarithmic equations. So let's do a couple of examples. In our first example, we have an exponential equation, and I'm going to solve this two different ways. Occasionally, you're able to rewrite both sides of the equation so that they have the same base, and I am able to do that with this equation because 81 can be rewritten with a base of 3. So I can rewrite this as 3 to the x equals 1 over 3 to the 4th power, but I need this quantity to be in the numerator to match the left side of the equation. 3 to the x equals 3 to the negative 4. Now that the bases match, I can equate the exponents, so x has to be negative 4. Now I'm going to solve the same equation using logarithms. 3 to the x is equal to 1 over 81. I'm going to use this property of inverse functions, that log base a of a to the x is equal to x. So since I need to release x from its exponential position, I have to undo its relationship with the base a. I'll apply logarithm base 3 to both sides of the equation. Since these are inverse functions, they cancel each other out, and x drops out of that exponential position. Now I have log base 3 of 1 over 81, but I am going to write 81 with a base of 3. 3 to the negative 4. Once again, these are inverse functions of each other, which means x is equal to negative 4. Now let's solve a logarithmic equation. I'm going to use the property that says a to the log base a of x equals x. And as x is the argument of a logarithmic expression, I need to undo that relationship by exponentiation, and I have to use this base. So I'm going to exponentiate both sides with base 2. Now 2 to the log base 2, that cancels out as they are inverse functions, and x drops out of that argument. On the right side, I have 2 to the negative 4. So x is equal 1 over 2 to the 4th power. Therefore, x is equal to 1 over 16. Now for the calculus. Derivatives for bases other than e. The derivative of a to the x is equal to natural log of a to the x. So this does have the self-replicating property that e to the x does, but it's joined by the coefficient natural log of a. Similarly, the derivative of a to the u, where u is a function of x, will be natural log of a to the u, but then times the derivative of u. The derivative of log base a of x will be 1 over natural log of a x. Remember that the derivative of natural log of x was simply 1 over x, and we have that here, but the x in the denominator is joined by this coefficient natural log of a. And again, similarly, the derivative of natural log of a u, where u is a function of x, will be 1 over natural log of a times u, but then times the derivative of u, whatever that function is. Now let's apply these rules in finding the derivatives of these functions. The derivative of y equals 2 to the x will be y prime equals natural log of 2 times 2 to the x. The derivative of y equals 2 to the 3x, y prime will be natural log of 2 times 2 to the 3x, but then times the derivative of 3x, which is 3. So let's rewrite this as y prime equals 3 times natural log of 2 times 2 to the 3x. The derivative of y equals log base 10 cosine x, y prime will be 1 over natural log of 10 times cosine x, and then times the derivative of cosine, which is negative sine of x. We can rewrite this as y prime equals negative sine of x over natural log of 10 cosine of x. But since sine over cosine is tangent, we can write this in simplified form as negative tan x over natural log of 10. What about integration? Well, occasionally an integrand involves an exponential function to a base other than e. When this occurs, you have two options. Convert to base e using the formula a to the x equals e to the natural log of ax and then integrate, or you can integrate directly using the integration formula. The integral of a to the x dx is equal to 1 over natural log of a times a to the x plus c. Find the integral of 2 to the x dx. Using our integration formula, this will be 1 over natural log of 2 times 2 to the x plus c, which can be rewritten as 2 to the x over natural log of 2 plus c. The power rule for real exponents. By now, we're very familiar with the power rule, but when it was first introduced, the exponent was required to be a rational number. Now we're expanding the power rule to include real exponents, even irrational ones like e. So let's find these derivatives and, when necessary, use our newly expanded power rule. First, we're being asked to find the derivative of e to the e. Well, despite appearances, this is just a constant, and the derivative of a constant is 0. Now we're being asked to find the derivative of e to the x, our favorite self-replicating function, and of course that derivative is e to the x. Here we're being asked to find the derivative of x to the e, where e now is a number. We're going to need to use the power rule, which will give us e x to the e minus 1. And finally, we have y equals x to the x. In order to find that derivative, we're going to have to use logarithmic differentiation to separate the exponent x from the base x. So let's take the natural log of both sides of this equation. Then I can use the property which allows me to bring this exponent around to become a coefficient. natural log of y is equal to x times the natural log of x. Now, taking the derivative, I have 1 over y prime is equal to the derivative of this side, which is going to require the product rule. X times the derivative of natural log of x, which is 1 over x, plus natural log of x times the derivative of x, which is 1. This means that on the left side, I'm going to have y prime over y, and on the right side, I'm going to have 1 plus natural log of x. Now it's time to multiply both sides of the equation by y in order to solve for y prime. And I'm going to do so by multiplying by the original form of y, which was x to the x. So my left side will be y prime, my right side 1 plus natural log of x times x to the x. And rewriting this so x to the x is the coefficient, I end up with my derivative. Y prime equals x to the x times the quantity 1 plus natural log of x. Now let's look at an application of exponential functions. Compound interest. Let P be the amount of your deposit, T is the number of years, A is a balance after T years, R is the annual interest rate in decimal form, and N is the number of compoundings per year. We have two formulas. One is for a discrete number of compoundings, N times per year. A, your balance after a certain amount of time, will be P times 1 plus R over N to the NT. And if it's being compounded continuously, your balance will be P e to the RT power. So let's do an example. A deposit of $2,500 is made in an account that pays an annual interest rate of 5%. Find the balance in the account at the end of 5 years if the interest is compounded A, quarterly, B, monthly, and C, continuously. So let's just identify a few things. P is 2,500. The annual interest rate in decimal form, 0.05. T is 5, and of course N will be 4, 12, and then compounding continuously, we'll use the second formula. So let's look at letter A. Our balance after 5 years will be 2,500 times 1 plus 0.05 over 4. Compounding quarterly means N equals 4. To the NT power 4 times 5. And this is going to generate $3,205.09. Now let's do letter B, where we'll be compounding monthly. A is equal to 2,500 times 1 plus 0.05 over 12. To the NT power will be 12 times 5. And this will generate $3,208.40. Finally, let's compound continuously. A is going to be 2,500 times e to the RT power, where that is going to be 0.05 times 5. This will generate $3,210.06. More compounding, more money. That's it for today's lecture. Since so many of you are musicians, I thought it might be helpful for you to see how a flowchart could be used to organize your lyrics. God bless you, boys and girls.